Do I have sound? Ah, yes. Okay, welcome back, everyone. Thanks for coming back on time. One of the nice perks of being the chair of ELS is that you get to choose the invited speakers. And for this conference, I've chosen two invited speakers, both of whom I greatly respect and whose words in the past have challenged my point of view and made me think differently about things than I had previously.
This is hard.
Yeah. So I would like to introduce Sam Ritchie. Sam Ritchie is a dynamite, explosive character. So I think he'll charge you up a little bit, sort of like a Pentecostal preacher in some sense. But so at this time, I'll give you the floor, and you have 1 hour to dazzle us.
Okay, wow. Well, let's get this up. Let's get this up full screen. Am I a Pentecostal preacher? All right. Can anyone hear me? Does this microphone work? No. Really? No? Okay. Hello, hello. Let's see. Let me try to move it up. Hello, hello. Good?
Yes.
Okay, just let me know. I'll talk to them. I'll speak into this microphone. Okay, so welcome. I'm Sam Ritchie. I've been a Lisper for many years. I hope I'm received well here at this conference. I'm a Clojure developer, so it's a little off to the side. But I hope to learn much Common Lisp this week, and we share more than we don't. So this is a talk about this idea of code as communication. We're going to talk about a library I've been building to explore these ideas and go through some bullets about why this is important and on and on. Okay, so SICM utils is a computer algebra system I've been building for the last 18 months or so. It's written in Clojure. It can live in many different environments. It lives on the JVM. It lives in JavaScript. And this is we'll talk more about it later. We'll have demos, but here's just a couple kind of code snippets. We've got every arithmetic operator you can think of. We've got LaTeX rendering. The library generated these slides, so you can sort of live code presentations. And here's a little more advanced stuff. We've got automatic differentiation. We've got symbols named alpha sub 1, and there we go. They render great. A little type language that lives that we can call upon here. This is all open source, so as you go through this, just know that the goal of this is to get tools out that other people can use to do things like we're going to talk about here in the talk. So the agenda is, one, why build a computer algebra system? There's a lot of these. Not many, but this isn't a new idea. This is one of the first things people were doing with computing back in the 50s and 60s. I think code can be this fantastic medium for communication. This is an idea that's been out there that Gerald Sussman, we'll talk about, has championed. But, is this really all it's cracked up to be? What does it mean to talk about code as communication, and what are people doing about it? The promise is there. Code is something that we use to talk to each other, but it's also something that can perform. It's something we build systems out of. So in theory, this is like the best game in town. We're going to talk about some examples of current approaches, these literate programming systems and problems. And we'll talk about why it matters to get this right, why this is really, really important for the way we talk to each other and the way we write software. And then finally, we'll do a bunch of demos about what I've been doing about it. Just my little approach. So the algebra system is it's a port of an original MIT scheme system by this man, who you probably know here at this conference. He's the author of Structure and Interpretation of Computer Programs and one of the co-creators of Scheme. Gerald Sussman, over the last, 30 plus years, has been coding up this personal library. I'm not sure anyone else really works on it. There's a lot of people that have contributed, but it lives on his machine. It's an algebra system that can do everything from sort of any generic Mathematica style thing you'd want up to advanced Lagrangian mechanics, Hamiltonian mechanics, differential geometry. And he's written a number of books that show really just the tip of the iceberg of the system. There's a quote that I love from Structure and Interpretation of Computer Programs. Programs must be written for people to read and only incidentally for machines to execute. This is an idea I read years ago when I first went through SICP. It was very, very exciting. in 2015 or so, I found these other books. Oh my God, he took the SICP treatment and he went to physics. I've always wanted to learn physics well, like everybody has. So you pick these books up and they're monstrously difficult. It's really hard. So we have these kind of two poles. There's this idea that code's good for communication, and then these demonstrations that even when you write down all of classical mechanics and differential geometry using software, that doesn't really give you a free pass. So anyway, I was excited about these ideas, this idea of, well, we can have textbooks written in code. That's fantastic. What if all of our research papers were like that? At the time, all of these visual papers of reinforcement learning and machine learning algorithms were coming out. And I thought, why not, wouldn't it be fantastic if the paper could be a library? What are we doing? Everyone's had this thought about PDFs of, wouldn't it be great if the PDF were actually just a library too? So I went to work at Google X for this research lab doing machine learning work. It was a bunch of ex-physicists. My job there was building tools to go do research more easily and then communicate the research more easily too. So I thought this would just be like shooting fish in a barrel for, let's solve this problem. It's going to take a month or two. Really what I found was the tooling I'd worked on for years in industry, this tooling for big data and streaming computations and sequencing jobs, I thought that we'd have a different tool set in the research world. You have a simple idea, you go explore it, you iterate on that. Instead, what I found is basically researchers that were desperately fumbling with these tools like TensorFlow and things that were really built for large industrial applications and didn't have any outlet that looked like sort of a lab notebook that you'd play with and just accumulate work over time as a research lab. Notebooks, which we'll talk about, are obviously an idea that exists and people use those. But again, as I'll say down the road, there's this break point with all this stuff where when you want to do something complicated, when you want to send jobs to the cloud and scale things up, you're ejected from this Garden of Eden, from these nice notebooks. And you refactor things as a library, and then they can't be shared anymore, and on and on. So there's a lot of pain in the world. I think people are thrashing around with their build systems, kind of most of their, a larger percentage of their careers, and you may all feel this pain too, than we really want to be doing. Easy things are getting hard to explore because of these massive systems that you have to go poke to go make anything happen. I think it didn't always used to be this way. I think computing just adds this layer of intensity to the problem. This may be a little bit of a just so story, but as I was going through this sort of pain of, man, what are we going to do here? Investigating any idea is so tough in computing, even though it should be easy. I found this great book called A History of Vector Analysis. It's a little bit of a dense book, but it goes through the history of the discovery of complex numbers, the idea that a complex number can be mapped to a two-dimensional plane, and arithmetic on complex numbers can talk about geometric operations in a plane. And then the search for, well, can you do that in 3D? Yes, it turns out. Hamilton discovers quaternions. And what ensues is this 100-year-long sort of battle for how do you express the laws of physics as they were known at the time? What's the right mathematical language? So you have quaternions, you have Clifford algebra, which is now presented as geometric algebra. And a latecomer to this is matrices and vectors. This is sort of long after the complex number and quaternion approach. And I bring this up because at the time when all this was being debated, this is all done really in the public eye. You have these researchers and these scientists and mathematicians. Hamilton was like a celebrity. This guy's famous, and he's out lecturing on quaternions. He's got games based on them. There's just this excitement about what is the right language for mathematical ideas? How do we express these discoveries we've made about the world? And immense time is put into trying to make them elegant. And that's really done communicating to the public. There's this intense idea that that's the real result. It's not let's just make it happen and sort of turn the crank, as we can do in computing, but let's find the right representation here. I think this is different than programming language battles. It's really what's the soul of this enterprise. It did remind me of this, though. I'm not sure if you all have seen this comic. It's this, this individual wakes up and says, oh my God, I fell asleep reading this Lisp book. I realized that the whole universe had been coded in these structures. Everything is S expressions. This is the language from which God wrought the universe. And God says, no, it's not. I mean, it should be, but we really hacked it all together with Perl at the end of the day. So code is communication. This, after this era of vector analysis and this sort of litigation in the public eye about what's the right language, code comes online, and you'd think that this would make this process easier to do. You could have sort of the code performing itself in demos of this is the right way to do things. And we'd have this incredible culture of sort of performative mathematics. That doesn't happen. I'm going to give an example of the kind of state of scientific computing as I found it when I was porting a lot of things over for this library and trying to rewrite them in a nice style. So if you write numerical code, I apologize. Like, this isn't about everyone, but it's pretty common. Please send me your examples that don't look like this. OK, so this is a footnote from Scheme Utils. I was a little shocked. This is from Mr. Code is Communication, right? He says, we love Brent's algorithm. This is where you find it. It's in this book from 1973. It's really good. We don't know how it works. So I decided I was going to port this thing and make it look really good. And no one would ever say this again. So I went back. I did this backwards. I'll present it forwards. This is the original book. There's a nice description of what this algorithm is. The algorithm is for if you have a single variable function, I want to go find the minimum point on it. And give me bounds, I'll go jump to the bottom. There's different ways to do this, but Brent came up with like the killer way. This is the way everybody uses. So he's got a nice text description of the algorithm. And then this code, which I mean, I'm too young, I think is Fortran-ish, but it's, I don't know. We've got this nice algorithmic description that complements the text very well. So you go forward to, there's a book called Numerical Recipes in 1986. It pretty much just has a Fortran port of that book with these nice terse comments. It's like test for done here. Like, what does that mean? And my expectation was over time, this thing would be massaged and you'd get this better and better. Finally, at the end, you'd have this shining, probably functional, wonderful description of the algorithm. Instead, you find this whole thing cargo culted forward over the years. So here's C++ boost. Whoa, we got the golden ratio in here. It's so beautiful. There must be something, magical to discover. But it's like the same code and the same variable names too, because God forbid you change any of this stuff, because no one really knows how it works. I'm convinced that the author of this boost thing did figure out what's going on here, because he's changed the comments a bit, and they're pretty cute. Like, this doesn't say try and construct a parabolic fit to me. OK, we've got nope, try golden section and said, whoo, parabolic fit, things are going fine. Oh dear, point U is worse. Like, this is the caricature of comments in code, I think. It's like, it's not that helpful for understanding. It just shows that someone else did and then didn't help us along the way. Do a golden section. Oh, this is Python. This is SciPy. I mean, I guess on the one hand, this is what you should do. You should take working code and move it forward so we can all get the benefit of using this stuff. But this process of hacking out, how do we best represent Brent's algorithm in the public sphere, that just kind of went out the window. So do a golden section step here. Like, I think this comment's not on the correct line. I mean, I spent probably 3 weeks on this one algorithm. I'm going to do this. And scheme. Oh, look, we've got scheme utils. It's the same problem as before. It's just the exact thing ported, sets everywhere. If you like this stuff, like in the slides, I put the full functions for each one. Don't use the Python one because I'm sure I got the white space wrong. It's totally bonkers stuff. I won't show you mine. It's better, I promise. But you have to believe me anyway. So this is what the algorithm's doing. Just to be clear, is you start with some function, which is the solid black line. You've got endpoints, which here are 1 and 3. And the idea is, well, a slow but a guaranteed algorithm will sort of slowly hone in on the minimum. And Brent in his book says something like you're a sheepdog, cornering sheep and sort of herding them into the pen. He's got this odd, flowery, but still lovely to read description. So his contribution to this was you can alternate between these two methods of sort of honing in on the minimum slowly but surely, and fitting parabola to 3 of the 4 points that you have as candidates, or the 2 endpoints and then 1 of the 2 candidates, and just trying to take a jump directly to the bottom. So to the extent that you look kind of like a parabola locally, this is going to make you take these massive leaps inward. And then he's got a system for toggling back and forth between these big jumps and the tiny sort of herding in steps that you get. If 2 of the points are too close, the parabola will kind of shuttle all the way down to negative close to infinity. So you don't want to do that. So the picture's helpful, but the picture isn't tied to any code. And I was a little confused reading it because, let's see, like if you look closely, I think it's, 5 says the minimum of the parabola is at 5. Like, I don't think that's actually drawn at the minimum. You can't modify this. You can't change it or try out any of your own functions with this. So if this is helpful to you, it's helpful to the extent that you have a brain that's fantastic at understanding abstraction and just generalizing from what you see here. Or you already get it, and you've already suffered through the code description, and you go, yeah, this is a reflection of the thing I understand. So wouldn't it be nice, as we'll talk about, if this were actually a visualization generated from the code, which is sort of a logging thing you could turn on and off, just to refresh your memory even. You might say, so what? Like, we have all these algorithms. What's the point of understanding them more clearly? One thing with numerical stuff specifically that I found is many of these algorithms are extremely simple, or combinations of extremely simple ideas. Like Brent's algorithm is this way of honing in on a minimum. There's only a few ways that people plug together in different iterations. And you see clearly these sort of other paths you could go down once you get those core ideas. If you want to go do work or your system falls apart, if you just have the original code, like, good luck improving. But if you get this idea of jumping to the bottom with a parabola, you can go, well, okay, the idea there is I'm trying to get quickly to sort of narrow out my search space. What if I tried cubic? What would be wrong with that? It's just easy to plug those things in when you have components and you fumble your way to understanding, which is what we're all doing anyway. Well, I'll speak for myself, I guess. So I think it's a huge tax we're paying. If you want to go do work in numerical methods, you don't start with this, okay, I get it, and then I'll hone my understanding over time. You sign up for this massive road into the culture of numerical computing. So what do? There's some existing ideas out there for how we can properly use code as communication. We'll go through a few of them. Probably the most well-known one is Donald Knuth's literate programming idea. This is an idea I was just primed to love. It's like, oh my God, you can just produce a book at the same time as your code. It's going to be so fantastic. Has anyone done this or used these? So we have a few. I have 2. I've really leaned into this. I found that it's just hard for, well, we'll talk about the problems with this later. Let's just say for now, it's a great idea in theory. There's a lot of good books. The books that have been produced like this are these sort of treasured gifts. I'll get into my critique or my own personal struggles with literate programming down the road. A different sort of code as communication that I love this idea, is Seymour Papert and this idea of, that was embodied in Logo. His idea was, if you want to get across computational thinking and you want people to really sort of understand what we've discovered with the modern physics models we have and with computation, what you need to do is put them in these little tailored micro worlds where the things that have been noticed over the centuries by our top minds and people with this special insight are just on full display, and the system's available to tinker and play with. So Logo, many of you have probably played with Logo. You've got this turtle, you can make it walk around. This is the actual original Logo turtle. It's like a big honking mechanical thing, and you can get it to go draw on paper. I went looking for, I don't think you can find these anymore, like even modern versions. So a project I have like on the back burner is to go make like a little Raspberry Pi powered turtle, because it's so great. It's so much better than just the thing on the screen. It's a great example of, if you want to show someone an idea, then build a world that demonstrates the thing you noticed originally and let people discover it for themselves. Yeah, you can take this really far. Logo turns out to be this wonderful programming language. This is a book by Hal Abelson and Andrea De Sessa that it uses Logo to go all the way from the basics up to Einstein's field equations and differential geometry. Like, it's really hardcore. It totally works. And yeah, it's free online. So I guess I'll link to the PDF if this is the sort of thing you think you're into. And a big one, the most, I guess, out there example now of literate programming, of code as communication, is this notebook idea that Mathematica pioneered. Google Colab, Jupyter, this is kind of all around. I will posit that these aren't working well, and I say that only because I just don't see much work out there that is presented this way. It's not that kind of everything has shifted, so every paper is this interactive library. So like something's wrong with this stuff. There are these beautiful ideas that I want to work, and they don't seem to be working. Here's some ideas I have, observations I've made over time. We've got literate programming is really a one-way thing you do. I've understood something. I've crafted this beautiful narrative about it. Literate programming, you're meant to really lean into this nonlinear narrative. You can really have little stories all around and then the big novel. It's extremely intimidating for people to contribute to. And you really need to eat the entire experience to get it. And then to contribute back is this almost like personal attack on someone's beautiful sculpture they've made. That's probably not true in principle, but that's certainly what I've seen as you look at these systems where someone presents something and they just don't get anything back. Maybe errata, just the same way you publish a textbook. Science is multiplayer. When you publish these things like notebooks, it's very, very difficult to get the environment of the person who built the thing up in the first place. So you see a lot of these examples published, these explorable explanations that are almost like museum exhibits that are encased in epoxy, where you look at it and it's nice, it sort of sparkles, and I turn the crank and sparks come out, but I can't grab it, I can't play myself. That's not true for everything, again, but I think the experience you want is one where in a lab someone can write on the whiteboard, say you come up and we work together. And the cultures in which that works are ones where people have this machinery in their brain to go do a lot of sort of simulation and animation. If you have to get it out of your head, it quickly gets very, very difficult, as I've found in any situation I've been in where publishing sort of Python notebooks is something we try to do. Dynamic is too seductive. I think this is the problem with code is you get it running and it runs, it's great, and you had to struggle, and the whole cleanup process is just a pain. I think this is what is going on with the SciPy examples and things like this. It's like Brent's algorithm works. There's also this idea in the air that if you mess with it, you're just going to slow it down. No one's going to improve on the Fortran from back in the day. That also turns out not really to be true. Compilers are really good. And I guess a final critique is that I say real work doesn't happen here. I'm thinking of when you look at Logo, again, you've got this book that goes all the way through differential geometry, but I don't think differential geometers are using Logo to go discover new theorems and publish their papers. And I have found this throughout my sort of education and career that often you're in this toy environment where you're learning something. You're playing with a physics demo or a physics animation. And then you're kind of left high and dry when you move on from that. It can't follow you to your career and move around with you. And I guess a symptom is, as we've been talking about a bit, you get students saying, well, I want to learn a real language. I want to learn C++. I want to do this, something I can use in industry. Because there's just skepticism that these tools that are dynamic and wonderful can follow you around, and that you're really building a skill set and a portfolio for your life. I'll just click through these. Okay, so why care? I think the reason to care about this stuff, beyond productivity, beyond, well, I guess, yeah, let's say that. One is just reducing friction in getting work done. I come up with something, I share it with someone else. There's the friction of understanding, the friction of building the mental model. And in the way of all that is just the friction of Git and GitHub and editors and all this stuff that just has to synchronize to share anything. But I think beyond that, we've got we've discovered some pretty amazing things, like this computational fluid that we can make matter compute for us. And it turns out that computation can simulate physical processes like pretty well, even in the, on the phones we have and browsers. There's just these incredible crown jewels of society that we've come up with. And like, just artistically, it's a shame that this stuff isn't sort of celebrated and in the air. And I think a lot of the toil with getting code running is a big part of that. So yeah, there's a book called The Future of Education that I love that really links into this. It talks about education as this process of acquiring shared tools from human culture. I won't go through all this now, but this leap to understanding abstraction and getting that, okay, models can represent big systems, and you can sort of write physics down as lists of numbers and turn a crank, and then the new numbers represent the new system. It's totally not obvious. It's really hard for people to get. And I think breaking through and understanding what the hell any of this stuff means is like a massive human thing that is important to go, just get to as many people as possible. Okay, so what do we do? I wanted to do something about this. My clues for where to start were these literate programming textbooks that Gerald Sussman and Jack Wisdom had built that were backed by this big computer algebra system. So my mission became, and still remains, to port these books into an executable environment where you could read the book and every sort of, the book's filled with equations and things that are generated by scheme. The problem is you have to go type the scheme in and get your environment set up, and it's like, it's really hard to share anything you've built, let alone get anything running. So in theory, this is an executable textbook already, but not really in practice. My idea was to go convert these things into the most easily shareable possible representations. And that implies it's got to be in the browser. I need to be able to do some exercise, have it kind of animate. Maybe every figure in the book is animating. Wouldn't that be amazing? And when I find something good or do an exercise, I can just kick it out. It'll run for someone else. They can download it and mess with it and tweak. And this incremental understanding that really we have to go through would just be something that is very natural and simple. So I think textbooks, I just have this picture here. A textbook is also a nice example where I think if you get it right, a textbook, like there's nothing beyond what a textbook can do. You've got this multi-hundred-page example of mathematical exposition. It's just full of all sorts of figures and graphs. It's really this distillation in the classical mechanics case of, I guess, millennia of work that we've done. Exercises are invitations to go publish new work. You have to collaborate on them because they're difficult. There's teaching. So this is sort of nurse log when a big tree falls and it becomes the source of life for other things in the forest. That was the thought of like this massive culture bundle. If you can get that working and make it this example of tooling and ability to share, then like you're off to the races. People will just go pick that thing clean, and you won't have to come up with, how do I do this, how do I do that? The example of everything is in the book. And the thought was that would create is an environment where as you work and as you explore and are just uncertain and read papers and sort of try to type ideas in that you found, as a side effect, you'd get these explanations out that are shareable and explorable. Versus the thing now where really what happens is you do the real work and then you go afterward and you have to write the paper, and it's like, you're basically building a new artifact that's cut off from all the original stuff you made. So as a side effect, if papers could just sort of flow out of Emacs, just as a result of you being confused, this might solve the situation. Okay. I'm going to give an example of a physics thing that does, the hope is this will be really confusing. So because we're all Lispers, so I can't show Lisp because you all get Lisp, so it's like I can't invoke this confused feeling other than going to physics. So does anyone, some people must, does anyone know these Euler-Lagrange equations? Okay, so there's this observation that classical mechanics has generated about the physical world. And let's see how deep to go into this. The question that leads to the equation we have up here and then the following slides is, okay, well, when I throw a ball, when I move through the world, I'm moving in a way that seems like physically real and natural. So the question is, well, could you have some meter that if something were a little strange, would detect that, would say, well, that's a little off. And then more and more unlikely paths would sort of signal louder and louder with this meter. If that were an idea that ever made any sense, well, presumably what that would imply about the world is, okay, this function L that I have up here, that would be some property of like the entire path between two time points of a system. If I throw the ball and it looks normal, something has happened that's sort of a summation, an integral over this whole physical path. And the idea is, well, if the path is a little bit off, maybe the integral would, the sum total of all these meter readings would be a little bit higher. Otherwise, you could sort of sneak weirdness at one point. But this is really a property of like entire paths. Okay, so if that's true, then, well, the derivative, the sort of change of this integral from two time points would be 0. You'd have the stationary point where the only way to wiggle is sort of more up on the meter. You're at this stationary minimum. So the question is it possible to say anything just with these facts? The derivative of some integral of a function that maybe looks at time, position, and then velocity here should be 0. I won't go into all of it. It turns out you can, just with that, with knowing nothing else, make this statement about that abstract function L. This is the Euler-Lagrange equations. So this shows up in the classical mechanics book. Sussman says, what could this expression possibly mean? To me, it's an example of one of these beautiful physics expressions that when you start to look at it and try to write it down as code, like, does anyone here have a clear idea of what the types are in this expression, or even what the hell's going on? It turns out there's a type bug. Like, it doesn't really make any sense the way this is written. So what actually is going on is this larger equation. Like q and q dot here, the speed and the velocity are actually specific positions. Time's already been plugged in. So there's this partial derivative here. The d dt is like happening before the t's been plugged in. Anyway, it's just super confusing to go actually try to do any work with this. And to the extent that you can, it's because you already know this stuff so well that this is this impressionistic shorthand for something that's just going on in your head. To communicate it to anyone, you need to go unwrap all this yourself. So we'll speed through this. Sussman goes through this process of, okay, how do you make this thing tighter? Well, you don't have these like baked in q's and q dots in your derivative. You go to functional derivatives where, a partial of 2 means the derivative of the Lagrangian, this L function with respect to its third argument. As we go and just sort of replace stuff. I'll go into this in more detail for anyone that's curious, but basically you go through these substitution steps and you end up with this, this equation you can write down in code that unfortunately still isn't much more clear. But sort of in theory that you can go run this thing and get stuff out. And so an example here is this is a piece of code from my library. I took this Lagrangian, I plugged in this abstract function. The thing I get out here, if you stare closely at it, and I'll skim now to save time, this matches up with F equals ma. So you've got on the right side this derivative of a potential energy. On the left side, you've got the second derivative of kinetic energy is mass, and then derivative d squared of the path at time t is the acceleration. So anyway, like symbol pushing, and the system can do it, but I don't know, I wasn't convinced that like this has gotten much. I can't show this to anyone and go, look, code is communication. Look how much clearer the code is. Because it's really not. It's really not. A specific example he gives in the book is the example of simple harmonic motion. I guess the gotcha with the thing is the L function, it turns out if you write down as the difference between kinetic and potential energy in a system, that is the thing that over time is getting minimized. The sum of that difference, the universe seems to be trying to push that down. So if you take any system and you know where it is at the beginning and end, the path it'll take between the two will just match that. That will be the minimum possible thing. And to the extent that you mess with that, it'll look less and less realistic. So here's an example of simple harmonic motion. You get out this equation at the bottom when you plug in this L of 1/2 mv squared and then 1/2 kx squared for the harmonic oscillator. You get out this thing that has to be true at every point along the path. And this is if you don't know anything about the particular function, you can go derive Hooke's law. And this is the kind of thing the book does. It's like pretty symbolic and tough to understand. So I'm going to go and switch over to Emacs here. Let's see if I can make this work. We'll see if we can make this more clear. All right. Now let me look behind myself and see if anyone can see this. Okay, great. Okay, so this, what we have here is on the left, we have a closure source file. On the right, we've got a browser tab. And what the browser is kind of a notebook that's rendering the contents of the closure source file. And if I go change anything on the left side, I can call this clerk show command, and the notebook over here should go ahead and change. Let's see. Yep, the notebook over here will update. That should happen without me having to hit refresh. Let's see if that's still true. Let's see if my... OK, so we've got the Lagrangian that I had here before. I've got some initial conditions. And I've got this physics viewer that I built where just with a Lagrangian, you can plug it in, and you'll see, given some initial conditions, what the system's actually doing. So let's see. These are all built as components. I've got kind of a view here now where I can see the equations of motion that Lagrangian generated, and I can see a physical system that's actually getting kind of kicked around by that Lagrangian. So if I go through here now, immediately, this looks right. It looks like a spring's bouncing that thing around, right? Maybe. There's no gravity, I guess is something to point out. What you could do is on the left side, go up and add gravity. And let's see if this will work. Yeah, and immediately, the update shows that, OK, the first two, the x and the y coordinate stay the same, but now the z coordinate has this extra thing. All I did was I added an energy term for 9.8 times mass times the height position. And suddenly the spring is diving down now. It's going a lot lower than it was before. Typically, physics books will stop at these really simple examples because you just can only get so much in your head. Even that equation before is kind of a head scratcher. The beauty of being able to do this stuff on a machine is that you can take something like this. This is an exercise from the book that was. They ask you to go derive the equations of motion for a bead, a particle that's sitting on this sort of stretched sphere, this ellipsoid. You go through this exercise, and you end up with. This is the Lagrangian. It's this massive equation. And I think it's like a joke from Sussman. I think it's trying to point out how complicated this stuff can get, and that you'd never do this by hand. But it's simpler if you just have a sphere. You get this nice, beautiful thing. But if you let the sphere stretch out, the equations of motion are just, totally incomprehensible. I don't know what the point is of doing this exercise. So what this kicked off for me was a journey where eventually, what is exciting is this right or not? Given the Lagrangian, you can plug it into this physics viewer, and you've got, this bead that, sure enough, is slowly moving around an ellipse. You can, just as one other thing, say, well, OK, now my mind's out of being freaked out by the equations. I'm more in playful mode. I can go ahead and take that same demo and plug in a gravity potential. And if I refresh to really get it to start at the initial, you'll see that, yeah, this thing starts at the top, and it just starts to whip around. And it's this kind of fun, pleasant thing to look at. It looks correct. What we see here is something where the physics engine in your brain can look at this and go, this thing's right. I don't know what the hell's happening down here, but this is good. And so this is the beginning of an experience that I'm trying to create with this live textbook project, which is you've got all these systems you'd like to explore. Usually, you have to push through this abstraction boundary to go do anything. If instead you could come at it from just this sort of generative systems where the magic of, wait a second, I don't know if I got this across sort of clearly, but to go from the previous sort of slow particle to this example, all you do is add a function that kicks out a scalar, just adds a little bit of a number to the output of this Lagrangian, and suddenly everything just works. And so this playful element of like, well, can I set up initial conditions that are a little more wild, or what if I got sort of, just as another one, what if I put 2 beads on? I connected them by a spring. Wouldn't that be cool? And sure enough, like it works. You've got this wonderful, interesting behavior, which is a scene you can set to go do a lot. It turns out the beauty of classical mechanics is not like staring at the initial equation. It's this discussion of symmetries in nature and conservation laws. And this is just such a beautiful scene to go have in front of you as you go explore that stuff. So anyway, there's sort of more demos of the system. It turns out it's not just a physics system. It's this wonderful componentized thing where ideally it's available in every environment where you're taking notes and studying and just sort of exploring. And the LaTeX you generate and the sort of playfulness you have persists as S expressions and data structures that you can go share beyond without really any effort later. So, yeah, what else to, let's see if I can get back to my slides. Oh, final comment, I guess. The entire library is built out of these namespaces. So we're speeding here, but this is the implementation of automatic differentiation, and it's written almost as a paper. Over time, this will sort of gain examples and things that'll make it more clear what's going on. But read this and you'll get everything. So that's the goal here. Textbooks as library, and then library as textbook. And with these examples, hopefully, we'll either find out why this is never going to work, or we'll have a good example people can rip off from. And yeah, that's, I don't know how to make my slides come back, but so I'll show my speaker note version. This is like a big community project at this point. So thanks to Sussman. Colin Smith was the one who initially started this project. Clerk is the viewer notebook you see. That's a wonderful thing that's available. Yeah, on and on. So I already talked about what's next. So yeah, thank you. That's it.
Do you have any questions?
Do we need a microphone? Okay. A second in the back row, yeah. I'll just stare at you all. Well,
I missed the introduction. What is Mentat Collective and how is this related?
Oh, sorry. Yeah, I didn't say anything about that. Yeah, so after getting frustrated with this Google experience after a year and a half, I decided to just quit and do this full time. With 2 friends from Boulder, we started, I guess what we're calling a research lab, but there's this core project I'm talking about. The other question that this collective is trying to deal with is, okay, to the extent that this is useful, how do you get more things like this built? Right now I'm just doing this and putting all my time into it, but
What is this .edu.com?
oh, mentatcollective.com. I need to put I'll share a website on the slides. I think we don't even have a solid place yet. .com for now. Yeah. But this is the question: is to the extent that this is useful, a startup producing this sort of work isn't something that's very natural. Is this an academic project? Where do you house stuff like this, or how do you incentivize people and allow them to do work like this that needs to happen? But well, I don't really know if I can write a grant for that or justify it. So that'll be a question we investigate of. As people want to come in and play, what can we say to them?
So it's interesting to know how this project compares to other similar tools, like for example, Maxima, which is similar in some regards. So I can tell that you're more focused on the interactivity of the system more than what's behind. So that's my question. How does this compare to Maxima, for example?
Yeah, I think so. I don't have personal experience, like deep personal experience with Maxima or these other tools. I've used Mathematica quite a bit. The library is I would say it's not primarily focused. The original Sussman work that's 30 plus years is really, really deep. I mean, it's a 60,000 line of code library that has kind of anything you could want if what you're interested in is symbolic computation. So I don't know enough about Maxima to really kind of go head to head. This project, in theory, will be something that, for most purposes, is as powerful as Maxima would be, with the ability to declare new types and have the sort of other abstract types with their own simplifiers and their own compilers. It is a fairly straightforward extension at this point to get a simplifier that works on matrix operations, for example, and that can take the same function and compile it down to a GPU representation and be shipped off to a cluster. So it's built in this sort of modular, immutable way so that it can be like that, but also have these in-browser viewers. And the idea being you can take a small example of one of your matrices and stick it up in the web, but then have the whole power of the server available to go crunch and just push stuff up if you want.
I have a question. In the meantime, you can repeat my question, but when we see the simulation moving, what's being computed? Because you've already computed all the differential blah, blah, blah.
Yeah, good question.
Where's the time being spent in the calculation?
Yeah, good question. So
Repeat the question.
So the question is, what is being computed? What are we actually seeing in the simulation? It's so cool. This just got working a few weeks ago. What's interesting about this is, on the one hand, we have this generic slow function where you can pass symbols in and get out a LaTeX representation and show that. What you can also do is pass the same symbols in, because we're in Lisp, get the S expression out, simplify it, pull out common sub-expressions, do all this optimization, make a new piece of source code. That gets sent to the browser, just in a closure data structure that's shipped over. And there's a state-of-the-art, a wonderful JavaScript ODE solver in the browser that takes that, compiles it in the browser, and uses that to basically create a function from the position I'm at now to a new time and tell me what all those variables need to look like to match the differential equations forward. So the simulation is just looping and saying, okay, new time, new time, new time, new time, and just asking the thing for the next positions. And JavaScript is so fast now. Like I had a bug where I was passing, instead of deltas, I was always starting at 0. So the simulation was going 1 second at a time, 2 seconds, it was just accelerating. And it kept up fine. The simulation started to get more and more insane, but it didn't bog down in these 30-second bounds, 60-second bounds. So for many things, it's really solid. But the ability to ship functions back and forth to the browser, also have them do the same trick locally, synchronize state across the web is just like a Lisp. Why is anyone using anything else? It's absurd.
I have so many questions. Your presentation triggered me in so many ways, which is really great. But
thanks,
I'll save many of them maybe for coffee time.
Yes.
I'm going to ask 2 questions, and you pick whether you want to answer one or other. You talked about literate programming, and you said you looked at Knut's version of doing it, which is these gems. I think it was Doug McElroy who wrote this paper, More Shell, Less Egg, where he compared Knut's version to it.
McElroy.
He said there are other ways. And there are a lot of places in between. I mean, you said this is not where work gets done, but I mean, in my team, work gets done like that every day of the week, using literate programming where you have in small chunks.
That's great.
That's one sort of challenge that I'd like to hear how you respond to that. The other one was you talked about going to use notebooks, but what I saw you do was write like Closure and Emacs and use the browser as a display tool. I think in answering Jim's question, you kind of half answered this because you're using some JavaScript in there. But I wonder why you have to leave Emacs. Why can't you just display within Emacs? I mean, this is a Lisp conference after all. Yeah.
I know. This is the thing. I'm this Closure pariah. Probably a better developer could. I think all this stuff. Don't challenge me to say anything can't live in Emacs. I'm not going to do it. Obviously, Emacs can probably do all this. So the first question, I think that's great. I work this way too. I don't think literate programming is I think it's a wonderful idea. I think it's a great way. It's just been hard to talk anyone else into doing this. And I've found that people who love it, like it sounds like you are, and there's stories of the original Unix team. There's just such a writing culture. If you have that, it's great. Many people I've worked with just seem to see this extra step of writing and exposition as just such a hassle that has to happen afterward. And so if something is a part of the way you think, and it happens to produce sort of consumable output by other people, that's the best thing that you could do. So if a team's already on a literate programming bender, I love that. For the teams that aren't, the question is, well, how do you bait someone or sort of trick someone into accidentally producing these shareable, lovely things? And, oh yeah, the second question about the browser. Yeah, I think the browser's like not a great environment to have be the final thing. But the thing I ran into was I just wanted to share with, just say my family, like my dad. Look at this beautiful thing of polar coordinates, and look at this function I've got. And there's no way to do it. I can't get it over to him. So forget this sort of broad, general scientific publishing. Just sharing something interesting with someone that can sort of perform itself and live. I think the browser just has to be available as a viewer environment. But yeah, the more Emacs, the better. I think like that's the issue with notebooks, is you're forced out of your lovely home.
More questions?
So, at some point in the presentation, you showed some equations, and you made a comment. What does this even make sense?
Yeah.
The types don't even make sense.
Yeah.
And if I understand correctly, this is more the kind of dimensional analysis, more than types, strictly speaking. But you use the word type, and,
Yeah.
and it makes sense here. You don't actually seem to use types in your code.
Yes.
And so, how come? Since it was part of the original.
Yeah, the type issue in the first equation is, let's see. The type issue in blah, 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 if I can get to this. Yeah, the type issue here is that, okay, you have DDT, but there's no T involved because you've already, like, in this partial L of, Q dot, it's just not clear what the DDT is even targeting. So why not use types? I love types. I spent a lot of years programming Scala. The one like pragmatic reason is they just don't exist in the original library, and I wanted to really get everything working the way it did in the book. I think that now that I've like absorbed all this in my head, I think a layer of optional typing on top of this would make it much easier to understand. A challenge you get with that is the dispatch system is open, so you've got all these different extensible arithmetic operators, and so really properly having like generic typing for everything. You want it to feel nice. I think in a language like Scala or Haskell, it would be onerous. And I've written systems like this where it's intense for a library author to do this. I hope it will feel better for Clojure. One nice thing you can do, for example, is when you take a function and compile it down to a subset of types, suddenly the types get much easier. By plugging concrete things in, you can auto-generate these type definitions. I think it's a great idea. I think the promise of, well, how do we understand these things? One is by watching them like animate and actually like make the thing that led to the observation in the first place. Another is just the code that you can walk into with your editor. I can sort of meta dot into all these different functions and read their doc strings. And another is just the types. Let me go follow around what I mean. What is this variable even talking about? So yeah, it needs to happen for sure. It's just a massive project.
I think there's been a great issue in ongoing times about reproducibility of results, especially in academic papers. I don't think there is much concern in making your results easily reproducible. Do you see this tool being an answer to that, and how do you see it? I have made that same observation, as we all have. I don't know if this tool's the answer to that, but I think the ideas that are inspiring this project, I think, have to be part of the answer. Where you say, when you get to the end of a project and you've got this mess of code that you sort of hacked together and got working, then you have this time when you need to produce a paper. That's the point where it's already too late. You don't even know if the thing works. The charts you've made are these PNGs that you've produced off your initial stuff. It's just such a massive project to say, I'll go afterward and clean this up and release it. And all the anxiety that brings on for people of like, well, can this thing even reproduce what I don't even know, but I knew it was right at the time. So
It worked one time. It's still working out.
yeah, it worked one time. So to the extent that I think it'll only happen when it's like easier to do a thing where
oh, I need to go remake that graph. Well, I've got this whole immutable, representation of the computation. I can just share that and send it off again. I think that's going to be a better way forward than, oh, let's just make Docker containers that get printed and stuffed away somewhere every time I do anything. That I've just found to be, it's so difficult to even reason about. So yeah, I hope things like this will be the way forward. To the extent that you're sharing constantly and everything's backed by immutable data structures, that's got to be the thing.
One more question?
Yes, one more question. I was thinking about the real work, as you spoke in the initial part. Sometimes the algorithms as just a snapshot, a projection, actually, from the whole equations, because they need to be faster when crunching numbers.
Mm-hmm.
So my question is, what about real work? We want to be literate about showing things in the presentations, but we want perhaps a different algorithm that does the same thing, that basically gives the same results, but we want it to be 2 times faster, 5 times faster, etc. So for that, the algorithm has already been cut down. It has been already just a result of variables that have a few comments here and there in Python, in Rust, etc. That's like going backwards, right? You have to look at the projection of the algorithm and try to understand the equations outside.
Mm-hmm.
But is literate programming a good thing to do the opposite? So we have the great stuff, the big equations, and go down the smaller equations. And how can we be sure that the second optimized version gives the same results than the first?
Yeah, that's a great question. It comes up a lot when you look at the source code for scheme utils. Sussman will have the real version of the function, and then the slimmed down pretty one that you want to display in the textbook. And often that really removes a lot of the complexity of the actual thing, even to the point of getting comments in the doc string, totally excised from the definition. So the 2 quick comments on that are, one, what this demo was doing with these generic sort of literate programming available versions of algorithms, yes, are going to be slower than the beefy stuff that you've hand-coded. You can get pretty far, it turns out, with this sort of, Julia does a lot of this operator overloading, where, okay, I'm going to pass symbols in and then go work on the source tree and eval a better version of the thing. But that's not going to be as good often as the hand-coded version. So I have some thoughts here on, well, if an environment lets you take the basic thing and then write a couple more complicated versions, one thing you could give someone that would make that just a natural thing to do is a test suite that gave you generative testing for free, looked at the types, figured out what to go throw at these things, and then automatically you got as tests, just this implementation matches this one, matches this one. That's something that's like good practice to do now, and often you'll find nice simple versions of functions in a test suite. But the problem I found is that means they're out of the normal narrative flow. So I think the style I'm going to try to experiment with here is give people tools that make stuff like that. It's just a gift. You're just going to get better testing. It's like you want the simple version anyway and the really complicated version. But then have a separate parser that says, okay, also what you've gotten out of that is exposition and literate sort of demonstration for people for free. So write the nice thing for your own sanity, write the crazy thing so you can get fast code and then also correct code, but also literate, readable code. I don't know if we have time for one more or all done.
Maybe we have time for another, but I think
Oh.
It's not a question, it's a comment. Suppose you take literate programming, aspect oriented.
Microphone.
So if you take literate programming and put AOP, aspect oriented programming on it, then you might solve the problem of the nitty-gritty details that Sussman didn't want to include in his book on quantum mechanics.
Okay, I'll take it. Okay, I think that's,
Okay, so thanks, Sam, for
yeah. Thanks, everyone.